Hello everyone, welcome to my YouTube channel. In this video, we are going to see some more questions from engineering mechanics, and the topic we are going to see is system of forces. The first question is, two like parallel forces are acting at a distance of 24 mm apart and the resultant is 20 Newton. If the line of action of the resultant is 6 mm from larger force, the two forces are option A 15 Newton and 5 Newton, option B 20 Newton and 5 Newton, option C 15 Newton and 15 Newton, option D none of these. One of the application of moments is to find the position of the resultant force. We can use the concept of moments to find the position of the resultant force. For that, first we need to find the resultant force. We can do that using any one of the methods like law of parallelogram of forces, law of triangle of forces, or analytical methods. And then in order to find the position of the resultant force, we need to equate the moment of the resultant force about any point to the sum of the moments of the component forces or individual forces. Okay, then we can get the position of the resultant force. Okay, this question is similar to that. In this question we have two forces and which are parallel and like. Okay, let these forces be P1 and P2 and these are acting at a distance 24 mm apart. So the resultant force is simply given by the equation P1 plus P2. So P1 plus P2 is equal to 20 Newton, which is the resultant force. Okay, now equating the moment of the resultant to the sum of the moments of the individual forces, will get 20 into 6, because in the question it is given that the resultant force acts 6 mm from larger forces, and we are assuming that the larger force is P1, which is acting at point A, so that 20 into 6 is equal to 0 plus P2 into 24. Okay, because since we are taking the moment about point A and the perpendicular distance between the force P1 and point A is 0, we did not write the moment of the force P1. Simplifying, we will get P2 as 20 into 6 divided by 24, which will be equal to 5 Newton. And from the first equation, that is P1 plus P2 is equal to 20 Newton, we can get P1 is equal to 20 minus P2, which will be equal to 20 minus 5 equal to 15 Newton. Therefore, the correct answer is option A. The forces are 15 Newton and 5 Newton. Now the next question is, three forces acting on a rigid body are represented in magnitude, direction and line of action by three sides of a triangle taken in order. The forces are equivalent to a couple whose moment is equal to option A, area of the triangle, option B, twice the area of the triangle, option C, half the area of the triangle, option D, none of. In this question, the three forces are represented in magnitude, direction and line of action by three sides of a triangle. Let these forces be represented by the triangle ABC, and let CA represent P1, AB represent P2 and BC represents P3. Okay, then applying triangle law of forces to forces P1 and P2. If we look at this figure, P1 and P2 are taken in order and these are adjacent sides of a triangle. Then the resultant force is given by the third side taken in opposite order. Please note that P1 and P2 are acting at point A. So the resultant of P1 and P2 will be equal to BC and taken in opposite order. So I have drawn the resultant of P1 and P2 through point A and I have named it as R1, and the magnitude of R1 will be equal to P3. Okay, because applying triangle law of forces. Now this system of forces can be reduced to the second figure. Okay, we have two forces having magnitude equal to P3 and acting in opposite direction. So this system of forces will be reduced to a couple, so that the moment of these forces will be equal to the moment of the couple, which will be equal to P3 into the distance between the lines of action of these forces, which will be AD. Okay. Now P3 is represented by the side BC. Therefore, we can say moment of these forces is equal to BC into AD, which will be equal to 2 times the area of triangle ABC, because area of triangle ABC is equal to half into base BC into height AD. Therefore, the correct answer is option B. 3 forces acting on a rigid body are represented in magnitude, direction, and line of action by the 3 sides of a triangle taken in order. The forces are equivalent to a couple whose moment is equal to twice the area of the triangle. Now the next question is, if a body is acted upon by a number of coplanar non-concurrent forces, it may, option A, rotate about itself without moving, option B, move in any one direction rotating about itself, option C, be completely at rest, option D, all of this. Before moving into the question, we need to see some concepts. The first one is how to represent a force in the 3D space. Okay, we can represent a force as F is equal to Fx I cap plus Fy j cap plus Fz k cap, where Fx is the magnitude of the component in x direction and I cap is the unit vector along the x direction. Similarly, Fy is the magnitude of the component along y direction and j cap is the unit vector along y direction. Similarly, Fz and Fk. Then the magnitude of this force, which will be equal to square root of Fx square plus Fy square plus Fz square. The direction of this force is specified by the direction cosines. Cos alpha is equal to Fx divided by magnitude of F, cos beta is equal to Fy divided by magnitude of F, and cos gamma is equal to Fz divided by magnitude of F. Okay. For examination point of view, direction cosines are not so important. So we'll move on to the next concept. We have already seen that a force is a transmissible vector. Okay. This means that a force can be moved to any point along the line of action of this force. Okay. And there will be no extra effects, or the effects will be same as before. The only condition was that this new point should be rigidly connected to the first point. Okay, but we can also move a force to a parallel line of action. Okay, but we cannot simply move that force, we need to do some more. If we look at this figure, we have a force at a point A along this line of action. Okay, if we want to move this force to a parallel line of action through point B, then first of all consider that at this point B there are two equal and opposite forces acting at point B. Okay, then if we look at these two forces, okay, these two forces constitute a couple. So we can replace these two forces as a couple. So if we want to move a force to a line of action parallel to the initial line of action, then we need to introduce a couple. This will be having a magnitude equal to F into D, where D is the perpendicular distance between the lines of action. Okay, so this is the new concept. Now moving on to the question, we have a number of coplanar non-concurrent forces. Okay, if I have a coplanar forces, we can also have so many forces as well as coupled, because two forces in a plane which are equal in magnitude and opposite direction and acting at two different lines of action will be constituting a couple. So this coplanar system will have forces or couples, and let this plane be xy plane, so that we'll have a number of forces F1, F2, etc. and we can also have couples C1, C2, C3, etc. So taking the resultant force, okay, we can take the resultant force firstly by moving all these forces to a common point, say origin. Okay, and then using the principles like polygon law or any other analytical methods, etc., we can find the resultant, and the resultant force will have the equation as Fr is equal to sigma p fx I cap plus Fy j cap, where Fx is the components of each force along the x direction, as well as Fy is the component of the all forces along y direction. Okay, we have to sum it to get the resultant force. Similarly, the resultant couple can be obtained by adding all the couples and also the couples that was a result of moving these all forces to the origin. Okay, now if you see, the simplest resultant of this coplanar system will be either a resultant force along xy plane and a couple. Okay, we can reduce the whole system into a single resultant force and a couple. Okay, and this system constituting a single force and a couple can also be reduced to a single force. Okay, we have already seen that if a force is moved to a different line of action, there will be a couple. Okay, now similarly, a force and a couple can be reduced to a single force by moving the line of action. So one of the simplest resultant of this case is the single force with a specific line of action. Okay, in order to solve this, first of all, we took all these forces to origin, and we will get a resultant force as well as a couple. But this resultant force and couple can be again reduced to a single force by moving the line of action of the resultant force away from the origin. So one of the case for the or first case where the resultant force, in the first case we can have the simplest resultant as a single force with specific line of action. Okay, in xy plane, that is the first case. Or what if the sum of the resultant force is 0? We can have the sum of the resultant force or the resultant force as 0 vector. The components along x direction can be 0. Similarly, the components along y direction can be 0, so that the resultant force can be 0, whereas a couple exists. Okay, then the simplest resultant of this case will be simply a couple. Okay, that's the second case, and then there can be also a third case, okay, where the couple can also be 0. Okay, so a number of coplanar non-concurrent forces can be reduced to either a single force with specific line of action or a couple, or it can be a zero vector. Okay, so if we have a single force with a specific line of action, we can have a translation or movement in one direction along with rotation. Okay, and then if we have a couple, then it can rotate without moving. Then if the resultant is 0, then the body can be at completely at rest. Okay, so the correct answer is option D. If a body is acted upon by a number of coplanar non-concurrent forces, it may rotate about itself without moving, move in any one direction, rotating about itself, be completely at rest, because the simplest resultant of such a case will be either a single force with specific line of action or a couple or 0 vector. Okay, now the next question is, the simplest resultant of parallel forces would be option A, a force only, option B, a couple only, option C, either a force or a couple, option D, both a force and a couple. We have a parallel force system. and let these parallel forces be parallel to y-axis. So we have forces F1, F2, F3, etc. parallel to y-axis, as well as we have some couples, say C1, C2, C3, etc. and these couples will be having a direction perpendicular parallel to z direction, because if we see these couples as forces, these forces will be parallel to the y-axis. Okay, so the simplest resultant of these forces can be either a single force with a specific line of action, or a coupled moment, or a zero vector. Because applying the concept, first we need to translate or transfer all the forces to origin. Okay, as a result we can get this resultant force as sigma fz k cap. Okay, if we add the component, there will be only one component. Forces will be having only one direction, therefore we can just simply add the forces and we will get the resultant force in this form, having direction k cap only. Okay, then the resultant couple will be equal to the existing couples as well as the couples that that is a result of moving the forces to origin. Okay, so the simplest resultant can be a single force with specific line of action, because as I have told earlier, if we move these all forces to origin, we will get a resultant force as well as a moment, and this again can be reduced to a single force having a specific line of action away from the origin. Okay, so that can be the first case. It can be a single force having a specific line of action, there cannot be a moment. Then it can be a couple moment alone, or it can be a zero vector. So the correct answer is either a force or a couple. Okay, the simplest resultant of parallel forces would be either a force or a couple. That's all in this video. Thank you.